you?
Hey.
Hey, how's it going?
Oh, how's it going? Oh, great.
Good.
It's almost evening here. So,
Oh, yeah, right. That's right.
yeah. So, is it so sunny those days in Carbondale?
Yeah, the last couple days it's been pretty rainy and stormy,
Oh,
but today's looking like it's going to be nice.
good, good.
75 degrees. So
You know, we're not a... Yeah, go ahead, go ahead.
where are you?
I'm in Saudi Arabia. Know that place?
Yeah.
Pretty hot, like Texas, Arizona, those states. Yeah, it's almost over 100, almost over the year. You know.
Oh my God.
Yeah, yeah. Sometimes it's you know how to convert the Celsius to the
Hello.
yeah. It's over 45 almost of the year. You know.
Oh my Lord.
Hi. Yeah. I think Dr. Shajish is accustomed to that. You know.
Accustomed to what?
To hot weather, when the temperature over 45 Celsius.
Yeah, above 45 is very. It's like saying in let's say in northern countries, people are used to negative 20 degrees Celsius.
Yeah, yeah.
Have it, but it's very rare. Like in India, probably 2 weeks in a whole year, and in those days, most of the times it's closed and other things, so people don't get out.
Yeah. Same here in Jeddah and Saudi Arabia. Same, except we don't have as much as rain as you have.
Yeah. What is the temperature there now?
Nowadays it's over 45, no less than that.
Wow.
Yeah, and it's dry. It's
Yeah.
only the humidity of the sea, you know. We Jeddah is in the west coast of Saudi Arabia, so that's the only you know. We don't have rains here. It comes like 2 weeks of the year, and that's the maximum thing.
And when it rains, it floods.
No way. Yeah. You know, when they build even the infrastructures of the city, they don't, you know, they don't take care of the rains. You know, they don't care about it. So.
Yeah. Okay, did the camera change? Okay.
Yeah.
Yeah.
So.
Yeah, go ahead.
Yeah.
Yeah, move the camera to. So
hi.
To each other. Yeah.
Hi.
Okay,
Are you guys all of you from Illinois or somewhere else?
I grew up in St. Louis, which is in Missouri, just a couple hours away.
Yeah.
I'm from Iowa, so just up north.
Wow.
Where in Iowa?
Dubuque.
I spent 1 year there in Ames.
Oh, gotcha.
Yeah.
I'm from Kansas.
Kansas State or Kansas City?
Southeast Kansas, small town.
I see.
Town
because the football team there in Kansas City, many of people think it's from Kansas, but it's in Missouri.
Right.
So
exactly.
yeah.
We don't have anything.
Couple of friends there. So nice meeting you guys.
Yeah, it's nice to meet you too.
You're slightly off. Okay, maybe I should try to catch it. Okay, there you go. You're really maintaining social distancing on the screen at least.
Huh.
The farthest 2 points on the flat surface. Oops.
Yeah, I guess like five or six people have been confirmed at SIU now. Is the case?
Yes, that's correct. 6 people confirmed, 3 non-resident students, 2 resident students, and 1 faculty or staff. That's what they say. That's what the website on SIU says.
I read the article in the paper, and a lot of people think, I guess, a lot more people are gonna get it. I don't know.
Yeah, I'm sure. I also heard that I think it's called Williamson County, right adjacent to us, John A. Logan College. They had 50 cases of that. It's a smaller town. And it's suddenly in one day 50. Like it was all going few cases per day. That's what I was told, but I'm not sure how genuine that information is. So check it out.
Williamson County?
Williamson, right?
Just
Cotterville, have you heard of?
Yeah,
Yeah.
Can you go to Marion from here to there? Like this is 10 miles.
yeah.
Like adjacent.
On the way to Mary?
On the way to Marion, you go through a small town called Cotterville.
Okay.
Hardly maybe 2 miles by 2 miles.
Right.
So I think Marion, all that fall into the county called Williams. And they don't at least it's not easy to access the data there. Like Jackson County maintains a very nice website, so every day they put the data in there. So Williamson doesn't do that, so we don't know exactly. Or I wanted to check it immediately, but I couldn't. Or I spent a minute of doing it. I shouldn't say that I couldn't. The minute I spent, I couldn't find much information. So yeah, be aware of that.
Yeah.
Okay. How is everything in general? Any comments on that? Did we have a homework today? No.
Well, it was due Tuesday, but you extended.
Today, so
Yeah.
so did everything work out? Did you guys? Okay. Yeah. Okay. I didn't check. Now that we submitted homework 1, so any comments on how the course should go? Is this how can we keep going? This basically repeats. I teach something, homework, repeat something, homework. So that will be the and be relaxed about the whole thing. But at the same time, if everyone submits and if you're the only one who has not submitted, that acts against you. So if you want any postmortem of any kind, you need to get together and inform me. So if I feel that the whole class is struggling or wants to postpone, then that's okay. But one person usually, at least even if it is one person, you can always approach me and say that, oh, I heard that. That's a good way to do that. So it's a small class, I can adjust as far as factor. But again, this is first few classes I think I've seen that usually things are reasonably easier than as we proceed forward. So I expect that you guys should all be doing whatever is necessary. Okay, what else? Yeah, so I don't see anything else. There's the homework 2 that's due Tuesday. Number 1 Tuesday, and you have midterm 1. September 10. 1 makes it 8. Yeah. Okay. So Khalid,
Yeah. Yeah.
you should meet me we should talk about how you're going to take the test, right? So some simple, reasonable, think of a crude way how you can put your camera and
Yeah.
all of us can
Sure.
watch you taking the test, something like that. Okay, so that's something.
Sure.
Again, not very official, not a sophisticated version, but just some. If you can arrange a camera that aims at you all the time, that should be good enough. All of us can see you.
Yeah.
Something like that. Okay.
Yeah. Sure.
Okay. Yeah, we were doing curvilinear coordinates. We just started on it. So idea is that how do you, if you don't start with anything, including rectangular coordinates, you have no information about what the space is like. For example, a classic example is space-time that we see. Like usually space, we have a very good feel for, an insight is there that it is 3 dimensions, you look around, however it looks like. But the moment you say, I'm thinking in terms of space and time, it's not very clear what kind of a combination is that. Is that orthogonal, not orthogonal? How does it evolve? So it puts you completely in the dark, and that's where these kind of approaches help, where you don't know much about the system, still how much can you learn in terms of very arbitrary choices, like the characteristic of your space should not depend on a choice of a person. Like in this room, if there are 3 of us in this room and others across virtually, like all of us should be able to choose our own coordinate systems, but the conclusions you make should be independent of that. Or at least we should be able to talk about some conclusions which are independent of our choices. There will be things that are dependent on the coordinate systems, but interesting physical quantities are those that are independent of the choice of the coordinate system. They are usually called covariant quantities. Okay, so that's our goal here, and we said that if you have or if you pick 2 such coordinates, let us say one you can say is x1, x2, and x3. That's your rectangular coordinates, but in principle, it doesn't have to be the rectangular coordinates itself, and we use the letter xi to represent this. And there is another coordinate system, which is u1, u2, u3. Think of this as surfaces of constant u's and surfaces of constant x's, right? A family of surfaces is what we are talking about. And it's the same 3-dimensional coordinate system, or in general, any dimensional coordinate system. And we don't even, we're pretending that we don't even know how to measure distances in these space. As of now, we haven't said anything about that. In such a system, we said we can define unit vectors, so or basis vectors. We said not unit vectors. So we said we can define what is called covariant basis vectors, and that we define to be E of downsteps. Right? So covariant is subscript, so that's equal to partial derivative of the position vector as a vector, as it's a geometrical object with respect to u of I. So that was our definition of covariant basis. We also said what is contravariant basis vectors, and we defined that to be with a superscript, same letter E. These are vectors. So I here means there are 3 of them. I is equal to 1, 2, 3. J here. So, I can use the same I here. I is 1, 2, 3. There are 3 basis vectors, and this we said is the gradient of. That's our definition of the covariant and contravariant basis. We showed that once we have this, we showed that always, irrespective of which coordinate system it is, always there is an orthogonality respected by these basis vectors, and that is that E I dotted, that is, this is a mixed symbol. This is actually a tensor because this vector also has an index, and that is an index of the label. So that's a tensor. This is also a tensor. So it's a mixed notation here. So this is 2 vectors dotted with different INJs. INJ could be anything. So in principle, this is a tensor of rank 2 because there is a dot product. So this is a tensor of rank 2. That's a tensor of rank 2, but it's a contraction there. So 2 goes away. So 2 remaining. So it's a tensor of rank 2. Is that clear what I mean? So make sure you understand what I stated that. So what is remaining here is a tensor of rank 2, which is delta ij. So no vector nature involved. Vector nature is dotted. And that's your orthogonality statement. And we specifically did this for cylindrical coordinates and showed that for the example was a cylindrical coordinate system, and this comes out to be E1 was rho hat, E2 was this is covariant, so this comes out to be rho times phi hat, and E3 was exactly C hat. If you are doing contravariant in cylindrical coordinates, we showed last time that this is E1, this comes out to be again rho hat itself. Here we are pretending that we know what is rho hat. That's a vector that in general, if you are in an unknown space, you may not have that familiar things around us. So that's E2. This comes out to be 1 over rho times phi hat. So that's a small difference, and then but that's really the inverse of that. 3 is equal to the hat. And this being exactly inverse of each other, that's because cylindrical coordinates are orthogonal. Like not every are orthogonal in the sense that even these individual covariant basis vectors are themselves orthogonal. So here notice the way we have constructed these need not be in general orthogonal, these need not be in orthogonal, but the dual space together they are orthogonal. That's the idea here, but in general it doesn't have to be. But cylindrical coordinates are examples of simpler systems where this is in itself orthogonal space. And we did show that this is orthogonality statement. Next, we want to define what is a metric. So having directional sense, now we want to define what is a metric. Metric is a prescription, if you want, to measure distances in the space that we have. So once you So notice how it's working. There are coordinates, and now you say that I make a small change in my coordinate system. I go from one point to the other point. How far have I gone? So that's a sort of a question we are asking. And for that, and that is what we'll call as a metric. But before that, we should remind ourselves that we already defined what is a line element, right? So this is how we defined, if you remember.
So I have a question.
Yes, please.
The way you define the metric, it sounded like a scale factor. You said.
No, it is. I have not yet defined the metric. It will involve scale factors, but not yet. I have not defined the metric. I wrote it down, but then I erased it. I have not introduced metric yet.
Okay.
So maybe I should list the scale factor here, right? Okay. So what is a scale factor? Scale factor, in retrospect, it is related to the metric, but not always. Especially in orthogonal coordinate system, it is actually the like scale factor really relates to the metric, but not always. So we are going to be keeping generality here. So scale factors, good thing to list in this, is pretty much there in covariant basis vectors. So this will be defined as, let's say, HI, be defined as EI, magnitude of EI, right? That's the scale factor. I think that's what scale factors are. Notice it is with respect to the covariant basis vectors you have to do. For example, in cylindrical coordinates, if you do it with the contravariant, you will get the inverse of the scale factor. So it is necessary that we define it using the covariant. That's a definition, so nothing. But as John pointed out, this has something with the metric, but I had not talked about metric yet. So let me build it. Okay. So we did introduce what is a line element. Line element is a change in the position. So you start from a position vector, make a small change, that's dr. And this is equal to, so this will be equal to du I like this was our definition of, like this is how it began. We said that, oh, suppose we make a small change in the position, and then we identified this to be our covariant basis vector. So this is by definition du I E I. In fact, that is how we should visualize the small change in position. So that was our first observation. If you want, so we began with line element. Right. Now, this is where the metric comes down. So metric will be defined as, so let me write here, mixed, so for an example. So here actually H1 is equal to 1, H2 is equal to rho, H3 is equal to 1. So that is what it is. Mixing up. Sometimes you're doing example, sometimes you're doing general. So here, now being very general, so this is how you will define a metric. Metric has to do with the distances. Right? So how do we define metric? So let's, so this is a line element, dot the line element with itself, which is a geometric object now. A small change, this is independent of which coordinate I use. For example, here I could have used u, v, any w, any coordinate system that's on the right hand side. Left hand side is a geometric object change in position. One point in space with respect to a very close point to itself infinitely small, that's gr. and dot it with itself, that will be defined to be the length between those 2 points. And that length, now we want to see it in different coordinate systems. So we just, whichever coordinate we use, so this is UI, we just put that in here. So this is UI, and dotted, so this is dotted with I cannot use I again because I is repeated index, so this has to be J. Okay. Notice the dot here is between the vectors. So that's a vector that is getting dotted. So let me rearrange this quantity here. And this is DUI, DUJ. And putting the vectors together, it's EI dotted with EJ. Rearrange the parentheses so that I'm collecting the vectors in one place. This can be done in irrespective of which coordinate I am in, whether it is U or V. And now I define my metric. So metric is metrics in this way we are talking about. It's a way to evaluate the dot product of this distance. That's how we define our metric. That will be in terms of the components, the metric, which we'll call as GIJ, which is basically the dot product of the orthogonality sense inside the covariant. So remember, we agreed that it is not necessarily orthogonal. It's not necessarily orthogonal. If it was orthogonal, of course, this is orthogonality. But otherwise, in general, this could be anything. And this is defined to be the metric, often just the metric itself, or more. Okay, this is components of the metric. And often, you can begin from here and get everything else. So this is a cyclic thing. What do you begin with? In principle, this information, if you know the components of the metric, you can go back and get everything else. This is the most important piece in here. Or I should say, it is like saying if you know the function and its derivative and its second derivative and so on. So if you know the derivative, you know a lot about the function itself. So this has that feature in there. So the space there's a lot of information about the space if you know the infinitely small element. So this is a line element, right? So it's a derivative. It's the first derivative, but it doesn't know anything about the curvature, but it knows a lot about what are its neighboring points. Right? Calculus has to do with the neighboring points. So this metric has all the information about what is at each point, what is the neighboring point, what is the characteristic of the neighboring point. But that doesn't mean the next to next. You know the closest neighbors, you don't know the next to neighbors. For that, you need the curvature of the second derivative. So that's going to be the basic point. Okay, so that's your metric. So as an example, we immediately evaluate what is it.
So I have a question about what you
Yes. Yeah.
So how do you do it irregardless of your coordinate system? Like, how do you choose 2 points that would work?
How would you
Any
choose?
coordinate system?
How
Because
would you
it's like, yeah, like, does it have to be an infinitesimally small distance between the points in order to does that make sense?
Ask
You're
again.
measuring the distance for a function in a space, right?
Uh-huh. Think of cylindrical maybe again, like maybe you're asking what are these functions? So remember, there is this understanding that we know the surfaces, right? Keep cylindrical coordinate in mind. Rho is x squared plus y squared. This is given to you, or we observe this. Again, if you're thinking of space and time, what's the relation between space and time? So that is to be understood. Like Lorentz transformation is a connection between space and time, if you want. Is that what you're having in mind? That what are these functions?
No,
Yeah.
that's okay. I'll figure it out.
Ask again. Try.
Basically, my question is, do you have to, so how do you make the metric work for basically any curve, like if it's a curved surface or a flat surface? How do you, I don't know how to ask the question exactly.
How about this?
I'll have to formalize the question and I'll just email you.
Yeah. Maybe let me state certain things and maybe let me know if you feel more comfortable after that. Suppose I was not doing cylindrical, let's say sphere, right? I'm in the same three-dimensional space, but I use spherical coordinates, or better actually, you're on the surface of a sphere. Your world is limited to be on the surface of a sphere, like we sit on the earth, right? We are not allowed to fly away. We are mostly on the surface of the earth. So we are on the surface of a sphere. But sitting on this room, it is hard to say that this is actually curved. I don't know, right? So I mean, it might be flat, and like many in the olden days, it was assumed to be flat, right? So what you do is you make a very precise measurement, and from this point to the next point in the room, and see what is the distance between them. And you have to be really precise, right? If it was curved, you will be able to see that. And the idea is, let me go to this other space. So we are on the surface of a sphere, and we don't know, right? We don't know that we are actually on the surface. So that's the harder part. What are the two coordinates you will choose then? This is theta and phi, right? There's only theta and phi you will choose, and that radius is fixed, right? Radius is not changing, and based on your geometry, based on various things that you do, you need to get these equations clear. How you will get that is the hard part, but you have to figure out first that points in this space, I have to go to spherical coordinate system, but I have to keep r fixed. So if you allow me, so this is x is r cosine theta, sine phi. So r is fixed, right? Y is equal to r cosine theta, cosine phi, sine phi, and z is equal to r. Wrong, right? Thinking ahead. Sorry about that. So this is sine and this is cosine, correct? And now you say that, oh, r is equal to x squared plus y squared plus z squared. And theta, so this is the comes up. So this is tan inverse of, what is it? Z over x squared plus y squared, yes? Correct?
It's the other way around.
It's
Other way around.
The other way. Yeah.
Yeah, it's x squared plus y squared over z squared, right?
Yeah, it's correct. Yeah. Thank you. Yeah. Yeah, z is making the angle with the sinus denominator. Yes, thank you. And phi, right? So now, maybe your question is, where do I get the equations from? Right? This has to, you have to learn this by walking on the surfaces, by making measurements. how you figure that out is the challenge, is the bigger challenge. But you have to learn this connection between theta and phi. And r is constant. This is a constant. Now, probably you're asking, if I understand or if I'm interpreting your question correctly, you're asking, how do we begin? Like, if you're in an unknown surface, give me some functions. But that's a hard part. Like, for example, space and time, Lorentz transformation has to be figured out. Like, it took Einstein to figure that out, or Einstein or even Lorentz actually figured it out. But the actual interpretation that it was space and time was done by Einstein. So in space and time, it took a long time to figure out. So similarly, if you're an ant or if you're humans sitting on the surface of Earth, what is the actual surface? You have to figure this out, and then you can proceed. From that point on, once you have this, then you do E1, right? Immediately you will say that, oh, what is E1? I'll define this to be dr over, in this case, d theta, right? And E2, there are only two, right? Will be dr over d phi, right? So that means to say somewhere that is, with respect to some origin, I have this is r, and I make a small change in the r. How does your unit vectors change? And same thing do with E1 is gradient of theta, and E2 will be gradient of phi. Here, gradient has to be specified clearly, but it is like since we're on the surface, but it will come out correct if you just do it. Follow. So notice this is a prescription. At this stage, this is a prescription. And that's the spirit in which we are working. But where do you get this from? That's hard. That requires exploring the space itself. Is that your concern, or maybe I'm completely tangent?
It was helpful, but it wasn't my question.
It wasn't the question. Okay.
Excuse me, doctor. I have like a trivial question. Is the gradient should be always partial by partial x, even here, and y and z and so on?
No, in rectangular coordinates, it's partial x, partial y, partial z. But you can write the gradient in any coordinate system. Right? In that sense, this is a geometrical object. So I always say that something that is independent of coordinates, like here, the way it is sitting, you should interpret it as some operator that goes perpendicular to this surface theta equal to constant. That's the way you want to see. An operator that goes from constant theta to next constant theta. But of course, when you want to evaluate it, you have to work with some coordinates, then you will work with x, y, z.
Could you give us a little example of the gradient of theta, like, yeah, just to make sure I
gradient,
correct.
For example, in spherical coordinates, this will be equal to r hat d by dr plus theta hat 1 over r d by d theta plus phi hat 1 over r sine theta d by d phi. Is that familiar?
Yeah.
Okay. So this is but this is also equal to, it's exactly the same as I hat d by dx plus j hat d by dy plus k hat d by dz. Or if you want better, so these are the three coordinate systems usually we work with. This is d by d rho plus phi hat. This phi and this phi is different. This is 1 over rho d by d phi plus z hat d by dz. So that should help. But we typically work only in these three coordinate system. Most of, like 90% of education is done in this. These are the easiest coordinate system, but very useful. Most of the exactly solvable problems fall into this very easily. But you have to go outside this exercise. You can explore if you want this. Take an ellipsoidal coordinate system and try to get this operator in them. So that's an exploration you can make. but let's not go there here. That's asking too much. Okay? But that's something that can do. Okay, that helps. So, yeah. Jordan, you want to try again once more, or you want to?
Maybe you'll answer it as we go through examples. That's
Okay.
what I'm
Maybe.
thinking. Like,
Okay.
I don't know how to ask the question in such a way that you would have a good understanding of what I'm asking, I guess. So it'd be unfair to take extra time on it.
Yeah. Yeah, I don't know how to answer that. Okay, we'll see. Yeah, maybe as you say, as we proceed, maybe you ask them. Okay. So metric we said is this, right? Gij is equal to I dotted with Ej, right? Notice compare this with the maybe just to contrast it. That is I dotted with J, right? There's a difference in this. One is between a contravariant and a covariant, and these are covariant itself, right? Dotted. So there's a slight difference, but there's a connection between the two, which we'll see later. But let's do an example, right? In cylindrical coordinates, what is it? Let's evaluate this. This is again a tensor, so there are 9 components to this, right? So let's and we know each one of this. So this is equal to, let's say, E1 dotted with E1, E2 dotted with E1, E3 dotted with E1. Right, that's your metric. Writing explicitly.
So Pythagorean's theorem is a metric.
That's correct in rectangular coordinates, only in rectangular coordinates.
Okay.
Right? I think what you're saying is, for example, dr dotted with dr is equal to dx square plus dy square plus dz square, correct? That's a straightforward statement. But I want to write this as dx, dy, dz as a row vector multiplied with a column vector. Not only that, I want to also introduce 1, 0, 0, 0, 1, 0, 0, 0, 1 times dx, dy, dz. Good? In rectangular coordinates, this matrix that is sitting in between, that's the metric. Okay, but I want to ask now, if I am in what do you say, spherical or cylindrical coordinates, this is actually d rho, d phi, and dz. And there is something sitting in between here. This is gij. And notice this is not rectangular anymore. And the same thing on this side. D rho, d phi, dz. So the question is, what is your thing in between? It will have scale factors, as you recognized in one of your sentences earlier. But we are asking, this is the metric. Does that help?
Yep, that's exactly what I was wondering. Yeah.
Okay, good. Yeah, so that's what we are trying. So this is this, right? And this will have scale factors in it. It's very clear, right? There's d rho. This must have some distance in it. That's in the here. Right? That scale factor is inside here, and we will see what that is. It'll come out naturally in this construction. So this is a very generic statement. It is here, and that's what we're finding. Okay. So this is E2, E3. This is E3 dotted with E2. And that's an explicit way of writing this Gij for any coordinate system. But here, let's do E1. Now we know this, right? E1 dotted with E1. This is rho hat dotted with rho hat. This is 2. E2 is rho times phi hat dotted with rho hat. And this is Z hat dotted with rho hat. This is again rho hat, rho phi hat. E2 is rho times phi hat again. So let me write this as phi hat times rho. This is phi hat times rho, and this is Z hat dotted with phi hat times rho. And this is again rho hat, rho phi hat, hat dotted with Z hat. Okay. So in terms of known vectors, we know that this is orthogonal, but remember, these are because we are using known features of cylindrical coordinates. Otherwise, whatever this comes, it should. So that's why the learning experience is. So these are our orthogonal unit vectors. So this is 0, 0, 0. This is equal to 1, 0, 0. This is rho square. That's 0, 0, 0, 0, 1. Of course, in general, this will come out to be h1 square. In an orthogonal coordinate system, this will always come out to be h1 square. But in your homework, you do a case where this is not orthogonal, right? Then it will not be diagonal. In an orthogonal coordinate system, this will always be diagonal. For example, cylindrical coordinates are orthogonal. The unit vectors at every point in space are perpendicular to each other. Even spherical coordinates, they are orthogonal coordinate system. But you don't have to be working in that. Typically, we work in orthogonal coordinate system, and your homework deals with such an example, especially crystallography is a classic example. In that case, this won't be diagonal. So the metric doesn't have to be diagonal. Don't assume that. And again, compare this with this, right? So your scale factor, so in general, in an orthogonal coordinate system, if it is orthogonal, this orthogonal coordinate system, this will always be h1 square 0, 0, 0, h2 square 0, 3 square. And if that is the case, then you can always write, so if it is orthogonal, only if it is orthogonal. Otherwise, they don't come out to be diagonal. So if it is orthogonal, you can say this will be always h1 square du1 downstairs, right? Where is it? It's not upstairs. du1 square plus h2 square u2 square and plus h3 square 3 square. For example, in cylindrical coordinates, this is the rho square plus rho square d phi square plus dz square. Think of line element again. This is the line element of a small volume element you can construct using cylindrical coordinates. D rho d phi dz square. Right? That's your metric. In that small tiny volume element that you build, on a cylindrical coordinate system, what's the length of each side. Right? That's your metric. Right? And that's what I think, Jordan, you were trying to point out in the beginning, or you tried to convey that, oh, these are scale factor. Metric is nothing but scale factor. Yes, in an orthogonal coordinate system, it is pretty much conveyed using the scale factor.
So scale factors are from a point, and the metric is from. How could you relate the terms, but not?
If it is an orthogonal coordinate system, then H1, H2, H3 has all the information about the metric, right? H1, H2, H3. It has all that information, but it doesn't have all the information in general. Like, then you need to have the information that where it is sitting. But if I tell you that it's orthogonal, then it is, you know that it's diagonally sitting. But otherwise, that could be a complicated function of H1, H2 sitting here. Right? As you will see in your homework, it won't come out that simple. Does that help?
Yes. So basically, that answers my question from before too, because I was thinking like, okay, from like a 2D Euclidean space, the Pythagoras theorem is the metric, but then in like a flat space, you have what was that? The Minkowski space or whatever the.
Minkowski space is when there's a negative, the distances are negative.
Minus the distance squared. Okay. Yeah.
But you can make it simpler. The point is, if you're again in two-dimensional space, let's say this is classic on this whiteboard, right? And now you don't use this as your coordinate system. Instead, you use this as your coordinate system. One is this, and the second is the same horizontal. And now they are not orthogonal. Like a crystal is an example where you don't have that choice of orthogonality. Right? There's a natural coordinate system that you would say that are two steps. So that would be a sodium sitting there, chloride sitting there. There's a natural coordinate system there which are not orthogonal. But you still can measure distances using that grid, using that lattice. Right? But you have to use not Pythagorean theorem. You have to use, this will be not a diagonal metric. Right? It will be a non-diagonal metric. And that's perfectly fine. As far as you know what you're doing, that's perfectly good. But of course, diagonal are much more easier to visualize. So we are used to dx squared Pythagorean theorem. It's much more easier. And that's there in your homework. So I think that's a good illustrative example. So work on that. Think about that. Okay. Reasonable?
Yes.
Any other comments, questions?
Is that the row squared in the middle? Is that equal to the is it 1 at the end, or by any chance?
This one?
No, the row hat in the middle. Yeah.
Uh-huh.
Is it equal to 1? Yeah.
No,
like
this is not row hat. This is row square.
Yeah. You know, like, is it a dyadic or?
No. This is okay. So this is how you want to visualize this. Okay, so this is a cylinder, right? So cylinder is coming out of this board, right? Z is coming out. Now this is one constant surface, and another constant surface there. Right? And now choose this, right? So this is your volume element. It's Z coming out.
Yeah.
Correct?
Yeah.
And now this row here is this length row. This is row and this is D row. So this is, if you want, this is D row. Can you read that?
Yeah.
Row, D row. So this is this length. This is actual number or a variable of the coordinate, right? Not a dyadic. Or maybe you're asking this whole thing is a dyadic. Yes. Is that the question? But this quantity here is row, variable. Okay.
Yeah, I thought it was like the one before, like IIJJ plus
No, no.
IJJ plus KK. Yeah.
No, this is by this point, these are actual real variables, right? So this is the row. Like
I
this is
see,
more
I see.
general,
That
so
one.
we had to keep this. This is cylindrical coordinates, 1 rho square. And so on. So a good point is now you can almost guess, right? What will it be for spherical coordinates? What will be the metric for spherical coordinates? Right, for spherical coordinates, what is the metric? Just guess it if you want. That's your extra credit. That's it. Okay. What is Gij for spherical coordinates? Gij is equal to for spherical coordinates. Any guesses? What are the scale factors for spherical coordinates? Do you guys remember?
Yeah, we wrote it down. I wrote it down.
Yeah, so for spherical coordinates, remember ds square is dr square 1. Good. And
1R and R sine theta.
Yeah.
correct. So
R
r square d
is it
theta
R
square.
squared?
Yes.
So it's 1000 R squared 0
That's
0
correct.
0 1.
Gij would be, you just read this out, right? This is 1 r square sine square theta. I gave the answer for extra credit. With the understanding that this is r, like xyz, it is always understood that xyz, but now we have to specify that the first coordinate is r, this is theta, that's phi, right? And this is phi, that's theta, this is r, this is your xy choice in that. Okay, else? You can always go and ask what is it for a cone, what is it for an ellipsoidal coordinate. Cone doesn't specify the coordinate system. Let's say ellipsoidal coordinate system or spheroidal coordinate system or parabolic coordinate system. These are all classic coordinate systems which have been used for doing classic problems. Okay. That's metric. And what gets more complicated is, see, this is all very simple spaces. In space-time, it's common to have, like the simplest space-time is the flat space-time, if you want. There is a minus c square dt square. Right, so that's your metric. If you
That's
want.
the Minkowski thing.
That's the Minkowski space-time. So there's a metric sitting here, right? Immediately, you know, G. So you will often see in literature that Gij for this is you won't even write. So
So it's C. I thought the Minkowski though was like c squared dt squared minus dx squared, something like that.
what? Tell it again.
The Minkowski space, if you had ds squared, it would be c squared dt squared minus dx squared. Is that not right?
That's right. I mean, typically you work in one space, one time dimension. So you're saying that dy and dz is not interesting. Everything is happening in the x. Like think of all everything going in one direction. Right? That's the easiest thing to deal with. But in general, you have to deal with 3+1 dimensions. But often the textbook examples are in 1+1 dimension. By 1+1 dimension, I mean one space, one time dimension. Then you ignore this. But that is 1 and minus c squared sitting there. Often you set c equal to 1. So you will often see this even written as 1, 1, 1, minus 1. If c is equal to 1. So this is how you do it. All right. So this means that they are meaning this construction. This notation again changes. Again, we won't be dealing with it all. Sometimes you write 3 minus 1 and plus 1. those are all different choices of that perfectly fine.
Does that imply that the scale factor of the time coordinate is complex?
Scale factor, oh,
Is that?
oh,
So 'cause I'm thinking
I see.
if the metric of Minkowski spacetime is diagonal, like if you can write it in the form of that you've written
Mhm.
the other, so like h1 squared, du1 squared, etc.,
Yeah.
then like it looks like
No.
okay.
A simple thing is no, because a complex thing is more involved. Okay. I would say no. Okay. So, but think about, okay, see, again, we have to go back to the definition, right? In the first place, when I wanted to write this thing, where is this? Yeah, this was an independent definition. It's just that it's convenient to write the metric in terms of that. But here, it comes out to be negative times the squared quantity. Right. So,
I see.
For example, like, so this is an issue, right? If you begin with this, this is the distance we're talking about. Let's work in 2 dimensions, let's say. This is the, suppose we are working with dx squared plus dy squared, right? This has a meaning. Like we understand what dx squared plus dy, Pythagorean theorem that. Suppose someone told you so that there is another space that we are working with, and this is dx squared minus dy squared. It's completely thrown off. Right? There's a minus because this can be negative, right? There's a squared quantity you're talking about, and this allows negative numbers associated with that. So right there, there is a new phenomena involved right there itself. So it is not that scale factor is complex. I don't think that's a good interpretation.
Okay.
It is convenient. Often it is done in the sense that, oh, let me write this -1 as I square. So you don't. So this can be written as dx square plus. So you have I square is equal to 1, right? So I times dy square, right? And then we are in a normal space because positive metric. The distance is a magnitude of a quantity, right? It is expected to be positive. But in this space, it is not. And our space-time is a classic example where it is not in our understanding. And then you would say that, oh, I want to avoid the whole thing by doing this. But that's a big cheat because this will not have everything that this has.
I see.
So, and one has to be very careful. So this has more information than this. Okay. But there in literature, it turns out, right? So this is, when I say that this has more information than on the right, we are talking about mathematics, the complex plane mathematics. There is more information. But now physics, apparently, is able to capture everything if you do this. As of today, whatever we have done, okay, we have been able to capture everything in this space by replacing this I. Okay, so that's a mystery why that happens. You don't know, and this is often called, going from here to there, this is often called the Euclidean, what is it called? Euclidean rotation, yeah, this is a postulate, you can say. The postulate is that which is not proved, or this is just a, is that this Euclidean rotation, this is often called Euclidean rotation, like you're on a complex plane, you rotate your coordinate system. There is a meaning to that. Maybe you will understand that in the next 2 weeks or so. If you do this and do your physics in that, you seem to be able to capture everything. as of today, we have not learned anything new from this that you're not already got from here. That doesn't mean that that's true. So you can ask, is the Euclidean postulate? Yeah, this is called Euclidean postulate. Euclidean
Is it
rotation.
the Euclidean parallel postulate? Is that what it is?
Euclidean what?
Parallel postulate?
Probably not. This is again, it's
about rotations with
that again. Yeah, stated.
something about rotations and flat, like rotating. I've heard of that before, but something about rotating flat surfaces, something, or 2D surfaces.
We're not. So this is a coordinate system rotation. So the point is, usually if you're in a complex plane, x and y, right? So let's think of this as imaginary and real. I can talk about let's say a phenomena that's happening from here to there, but then that is equivalent to going from here to there. Okay, so this is not very obvious what I'm doing, but hopefully in the next 2-3 weeks, it's okay. Let us say that path C1, C2, C3, right? So there is some path C1 plus C2 plus C3. This is always 0 according to some law, right? We'll see that in the next 2 weeks. It's called Cauchy's theorem. If C3 was equal to 0, then C1 is equal to minus C2. That means to say going on the real line is equivalent to going on the imaginary line. And that's what here we are doing. Instead of going along the imaginary line, go on the real one.
Okay, I see what you're saying.
But that is not always true unless this is 0. Right? And usually we don't know anything about what is happening on that C3 curve. It is not always true, so we cannot say that. But again, as of now, whenever we do this, we are able to capture everything. So, and this is very non-trivial. There's so much richness in this space, and you're able to capture it from a flat or a very Euclidean space is remarkable. So it has been converted into a postulate that happens to work. Why does it work? That's, I think, to my knowledge, an open question. Many people have written various things on it, but I don't think it's a foolproof thing. That's nice things, right? While you're talking on this, there's only 10 minutes. So here is something that always enticed me. This is, do you guys know Kochik, Dr. Kochik? This was first stated, or I sat in one of his classes, and that's when I learned.
What was his name again?
This is a mathematics professor in SIU. His name is, what's his name? I don't call him this. His name is Urek, or he goes by Urek. So this is Jerzy Kochik.
Oh yeah, the guy that sends the emails for the math.
Yes, that's correct. That's correct. Yeah, if you attend potpourri seminars, yeah. Since some of you guys are new, so that's something I can at least I can tell you guys about. There is something called potpourri seminar. Actually, it's there today. So this is an informal group, reasonably casual. I will you agree? That it's
absolutely.
Pretty casual. Yeah, it's very casual. I would say very student driven, right? It is addressed to a student, not for experts at all. And it's a group of maybe 5 or 6 faculties or less than that, and maybe 6 or 10 students maybe. And they come off and on. Not everyone comes all the time. Very casual, so I'll encourage. So it's on Thursdays, 2 p.m. to 3 p.m. It's just some talks. So today they are going to talk about, since this is the first day and they didn't have any talks arranged, so they're going to talk about some mathematics books. Yeah, have you got the email?
It said they're going to restart the seminar today with an informal Zoom gathering, as one of the topics we may discuss is graphic novels on math.
Okay, right. So since you're reading that, can you forward that to others in the
Yeah.
the class? It is. I like the discussions that happens are informal, but it's not a requirement in this course at all. Don't even imagine that I'm asking you guys to come. But if you are interested in mathematics-oriented discussions, that's a place and nice, simple people. So please forward it, Jordan, and today at 2 p.m. And if you're interested in this talks, send an email to coaching or just send an email to me. I'll be glad to forward that to you. It's a nice set of people. But here is what he addressed, or I sat in one of his classes on geometry, I think 2 years back, and this is the point. So I might have asked this before. So what is, first ask, what are Platonic solids? What are Platonic solids? Oh, I'll not try to remember. What are Platonic solids?
Not sure.
Objects
Not
that
sure.
have
Something like
their sides are the same geometric shape.
Oh, you're very low in volume. Is it Michael? You were speaking. You were low, very low in volume. Can you speak a little louder or come get closer to the mic? Yeah.
Yes. Platonic solids are geometric shapes in which all the sides of the solid are the same shape.
Same shape, exactly. So, for example, I think you construct, let us say, in 3 dimensions. This is an edge, right? This is the same, like a cube, has the same length, right? Now can you think of anything else that has the same length? And you would say tetrahedron is one. How do you write tetrahedron? Again, same length L. And then ask, can you construct anything else? Right? Apparently, there are 5 such objects. One is octagon, right? Octahedron. And then there is a dodic.
Yeah,
Can you tell? What are the 5 ones?
I think
Dodecahedron is one.
Yeah,
I don't draw that.
Yeah.
And octahedron. That's also one. So 4. What is the 5th one? Oh, icosahedron. Okay, so that's the 5th one. Now, that's well-known statement. Okay. Suppose I were in 2 dimensions, dx square plus dy square. Right? What are the objects you can build, geometrical figures you can build, which has the same sides? Right? Example is triangle, a closed figure which has equal sides. Now we are in 2 dimensions, easier to draw, right? L, L, L. Anything else you can think of?
Square, maybe?
Square, of course, right? What else?
The diamond?
Diamond. Diamond, I think you want a closed surface that cuts, right? Probably you're talking about this way. That cuts, right? So we don't want intersection. Let's say a new rule again. You don't want intersection.
I mean, the diamond, isn't it?
Oh, rhombus.
Yeah, I think.
Oh, rhombus.
I think each angle has.
Yeah, so rhombus, now there is a new rule I'm going to bring in, right? So you're also, so there is a new rule now, right? So you are saying that, oh, this is also length L, right? So now I bring in a new rule. Notice this has more symmetry, like from every corner, everything else should look the same. Okay, so now I will change my rule. Okay, so that doesn't qualify. Okay? I'll keep changing the rules. But that's not me, okay, that's a Platonic solids. I didn't say it before, I think that's I was not aware. So rhombus doesn't fit in, but if you very quickly think about it, like pentagon fits in, or a hexagon, or pentagon.
Infinitely many polygons.
Exactly, right? So all of them come in, right? And you can keep going, right? All what are the polygons, right? Equal-sided equal-sided polygon. So that's great. That seems to be easy, right? Now here is the hard thing. Let's change the space. And now, even to imagine a triangle in such a space is hard. What do you mean by a triangle in a space which is having a metric that is dx squared minus dy squared? What is a circle to begin with? Right? In a space like this. And the question that was posed, and again, you need to have some idea of what the space is. I have not told you anything. It turns out, like for example, if this is x and this is y, exactly like Lorentz transformation, right? Dx squared by dy squared. So if I say dx squared minus dy squared is a constant, right? If the same thing was done on your this metric, you will think of it as spheres, and these come out to be hyperbole, like this, like this. Okay, and you can talk about distances here. And then the question is, what are the possible Platonic solids in this? And yeah, so how about this? That's the next
I guess the thing I don't understand is it seems like all the lengths go to infinity on this.
All lengths go to infinity. Yeah, I mean, good. But I don't know. By the way, this answer I think is, I mean, I shouldn't say open. I'm sure people have thought about it, and that is people have. I don't think it is written down. So if you can really get something interesting here, probably it's nice to write down. So the extra credit problem is what are the, I mean, don't spend too much time. Yeah, if you want, you can, but don't do it for grades. Okay, extra credit. At least this captured my, I was very curious. I explored this a lot in my own way. And so the question is extra credit, right? What are the Platonic solids in? So this is also called what is the space called? Yeah, it's connected to SU11, but yeah, let's not talk about that. Yeah, in what are the Platonic solids? Yeah, what are the Platonic solids in Minkowski space? Like it's a very advanced question for what I have posed, because I have not even introduced what a Minkowski space is. For that matter, for you guys should also find it interesting. What's a circle in Minkowski, or what's a triangle? What's geometry? What are angles in Minkowski space? It's amazing how much we depend on natural instinct. Or angle, that's trivial, right? What's the distance? But the moment you change a sign there, you're completely lost. Like, what do you mean by angle, or what do you mean by vector? Right? So it's good to ask those questions. I'll encourage you a lot, but it's not needed in this course at all. Absolutely not needed. If you don't know, or if you think that's all crazy, just write that. I'm not interested about that. Okay, that's good enough an answer for grades. Yeah. But if you're interested, go ahead and explore it yourself. And yeah, we'll stop here. And next time I'll do some more on this. I want to talk a little about curvature, but I'm still wondering how far to go. In the earlier semester, I've done curvature, but I think it can go very well. But I'll see, I'll try to simplify the concept a little. So I'll do this next week also, but I won't go too far into it. I don't know how far to go into curvature. And have you heard of Christoffel symbols?
Briefly, yeah, Christoffel.
Yeah.
Or whatever.
Christoffel symbols. So, Michael, have you?
No.
Aliyah? No. Oh, so yeah, then I should introduce it, even if it is just for, at least you should be familiar with the idea. So think of it as metric is the first derivative, and you want to take the, like, metric depends on the close by objects, right? I am here. How's my next point? What's my neighbor? How far it is? What kind of neighbor it is? And then that tells you velocity in a sense.
I wrote down something about Berry curvature or Berry.
That's correct. Yeah. I will talk about Berry curvature. I like to talk about Berry curvature, but in general curvature, for example, what's the curvature of space-time? How do we go around figuring that out? So we start with a coordinate system, and its second derivative tells you. So now these are the vectors. Now how these vectors change from one point to the other, that has information about the curvature of space. So that's the basic idea. So that sentence has everything in it, but now we want to formalize that. So how these vectors change from one point to the other, that tells you about the curvature. So yeah, we'll talk about that, and I'll try to make it simple, but it will get a little messy.
So is all this ways that we can, using metrics and things, way to like quantify the behaviors of space itself? Is that the goal? Like whether, regardless of if it's flat or curvilinear, but you can.
That's correct. That's correct. These are intrinsic properties of the space. Like the curvature, for example, is an intrinsic property of the space. Like you can say space-time if I make it extended. So the question asked is our space-time curved or not curved? Like that's a simple question if asked. These are the ways you will address it. Does that help?
Yes.
And you asked, like, I think this is also called connection. So this is I, J, K, or sometimes it's a opposite. So you can also say this I, J, K. This is called connection. In the modern sense, it's called connection. Earlier, this was called symbol. I think it's the name of a person who first derived it, but these days it's more common as connections. So first is so the three quantities of interest in a coordinate system is first comes metric, then comes connection. So this is, if you think of this as the basic entity, this is the derivative of that, and curvature is the second derivative. And Einstein's theory deals with metric. Like for example, in electrostatics, you deal with what is the electric potential, right? So the question we ask is, what is the metric of our universe? What is the distance measurement entities? That's decided by how much energy is there in the system, universe, how much mass is there in the universe. But those are all physics. We'll try to just, I think since you guys have not heard the connection and crystal symbols, so I think just to introduce this, it is nice. Even if a deep understanding of it may not come out from my lecture itself. Yeah. Yeah.
So when you take the metric of our universe, I guess as of right now, it comes off, and that's why they're like, you need dark energy or dark matter. There's something there that's not accounted for. Or is the metric correct and some other pieces incorrect?
No. So the point is, no, that is the right side. Okay, maybe I can explain this qualitatively. Okay, so for example, is this a familiar idea? I'm going to write an equation. L square phi is equal to rho. Right? Is that a familiar equation? Jordan? Okay, so let me write this. That's Laplacian equation. So Maxwell's equation is this: del dotted with E. The class has ended in principle, so if you have to go, so you can go. Don't feel obliged to be here, but and this is recorded, right? You can always. So this is Maxwell's equation, correct? Rather than epsilon naught here. Let's say epsilon naught is 1. Right. So this is del dot E is rho. Is that familiar?
Yeah.
That's Maxwell's. This is charge density. That's electric field. Electric field is negative gradient of phi in electrostatic circuits. Right. So this is negative gradient of phi. Okay. Now it's just an analogy I'm giving. Okay. Now the point is, if I have a charge, it decides what is the electric potential everywhere in space. Is that clear?
Yep.
Okay. Or if I have a charge, it decides what is the electric field everywhere in space. Correct? Now, a very poor man's Einstein's equation is del square. Okay, this is not del square. This is more complicated than that. That's a curvature and all comes in there. But a poor man's Einstein's equation is G mu nu. This is a metric, space-time metric. Mu because it's 3 plus 1 dimensions, right? This is a metric, right? This is equal to, the source is now, since it's a tensor, this is a tensor. So this is energy and mass. Energy, momentum, mass. 3 quantities. Okay. Now think of this: charge decides your potential. Very naively, how much energy is there in your universe, how much momentum is there in your universe, and how much mass is there in your universe decides your metric. That's Einstein's equation.
Okay.
Okay. Now we can measure we know a lot about our metric in different ways, right? And you can do the reverse problem and say that, oh, how much energy, momentum, and mass should be there. And it turns out we are missing 75% of 75 to 70, yeah, around that percentage. That's big chunk we are missing. Does that help?
Yeah. That's exactly what I asked. Yeah.
Yeah. So this is very qualitative. This is much more complicated, but a naive, simple man's general relativity is very poor man's. Okay. Anything else?
Thank you for that explanation.
Yeah.
Yeah, good. But again, simple. Okay, yeah. It's at the price of simplicity, or it's sometimes wrong, right? Some simple things are sometimes outright wrong, but that's okay. Like in very smooth places, that's okay. Yeah. Be careful what you do. Yeah. Okay, that's all. Thanks.
Okay. Bye.
Yeah. Bye. Bye, Michael. Bye, Elia.
Thank you so much. Bye.
Well,
Bye, Jaron.